Welcome to this lecture on adaptive radiation in mammals. Imagine having a basic block of clay that you can mold into a shovel for digging, a paddle for swimming, or a kite for flying. This is exactly what nature did with the basic mammalian body plan over millions of years. Today, we are going to explore how early mammals transformed their limbs to survive and thrive in completely new environments after the dinosaurs went extinct. To understand how this transformation happened, let us look at the world right after the dinosaurs went extinct. The world was suddenly empty and full of opportunities, like open forests, deep oceans, and vast skies. At that time, mammals were mostly small, shrew-like creatures scurrying on the ground. To survive and thrive in these new homes, they had to change their bodies, especially their arms and legs. This incredible process, where one basic design transforms into many specialized tools to fit different environments, is what we call adaptive radiation. It is like nature's very own Swiss Army knife. Now that we have a conceptual understanding, let us look at the formal definition. In evolutionary biology, adaptive radiation is defined as the rapid diversification of a single ancestral line into a multitude of new species. Each of these new species becomes adapted to a specific environmental niche. For mammals, the most striking evidence of this phenomenon is found right in their locomotory appendages, which are simply their arms and legs. As they moved into different habitats, the physical demands of their environments forced their limbs to adapt in extraordinary ways. This brings us to the anatomical evidence of these adaptations. Despite looking completely different on the outside, every mammal shares a common underlying bone structure known as the pentadactyl limb, which means a limb with 5 digits. Whether it is a bat's wing, a whale's flipper, a horse's leg, or a human's hand, they all contain the exact same basic bones, such as the humerus, radius, and ulna. Through the forces of natural selection, the lengths, thicknesses, and shapes of these bones have been drastically altered over generations to optimize for flying, swimming, running, and grasping. Understanding this shared anatomy leads us to an important question. Why does this matter today? Understanding adaptive radiation is absolutely crucial because it provides the clearest proof of how evolution operates through descent with modification. It shows us that nature does not invent new structures from scratch. Instead, it brilliantly recycles and modifies existing ones. In the real world, engineers and roboticists study these mammalian limbs to design better machines, a field known as biomimetics. For example, studying the elongated, lightweight bones of a batwing helps engineers design more agile and efficient flying drones. Now that we see the engineering value of these limbs, let us dive into the actual mechanics. To truly understand how a limb adapts for either speed, like a cheetah, or power, like a mole, we have to look at the physics of levers. A mammalian limb acts as a biological lever system, where the joint serves as the pivot point, or fulcrum. The muscle pulling on the bone provides the input force, and the foot pushing against the ground or water provides the output force. This elegant mechanical system is what allows mammals to perform such diverse physical tasks. To quantify this biological lever system, we use a fundamental physics concept. We measure the mechanical efficiency of this system using the mechanical advantage formula. The formula is MA equals L in divided by L out. Let us break down these symbols. MA stands for mechanical advantage, which is a unitless ratio telling us if the limb is built for power or speed. The variable L-in represents the in-lever length, which is the distance from the joint pivot to where the muscle attaches to the bone, measured in meters. The variable L-out represents the out-lever length, which is the distance from the joint pivot to the end of the limb. When L-in increases, the limb generates much more force. Conversely, when L-out increases, the limb moves much faster at the tip. Now that we have our formula, let us apply it to a real animal to understand its adaptation for extreme speed. We will calculate the mechanical advantage of a cheetah's leg. We are given that the distance from the cheetah's elbow joint to its triceps muscle attachment, our in-lever, is 0.05 meters. The distance from the elbow joint to the paw touching the ground, our out-lever, is 0.40 meters. We substitute these values into our equation, placing the short muscle attachment distance on top and the long leg length on the bottom. The final answer is 0.125. Physically, this very low number means that for every small contraction of the muscle, the paw swings through a massive arc at incredibly high speed, sacrificing pushing power to maximize velocity. Having seen a speed adaptation, let us now look at a mammal adapted for power. We will examine a badger, which digs through hard, compacted soil. For the badger's front leg, the in-lever distance is 0.12 meters, and the out-lever distance to the digging claws is 0.15 meters. Digging requires immense force, so we expect a different mechanical setup. We plug these specific bone measurements into our equation. Notice how much closer the in-lever and out-lever values are compared to the cheetah. The result is 0.80. This significantly higher value means the badger's leg operates like a heavy crowbar, translating muscle contraction into massive output force at the claws, perfectly illustrating a fossorial or digging lifestyle. To visualize everything we have discussed, let us look at this comparative diagram of homologous mammalian forelimbs. On the screen, you see 4 different limbs: a human arm for grasping, a bat wing for flying, a whale flipper for swimming, and a horse leg for running. Notice how the underlying blueprint is identical across all 4. At the top of each limb, you can see the humerus bone. Below that are the radius and ulna, leading down to the carpals, metacarpals, and phalanges. While the bat has incredibly elongated phalanges to support a wing membrane, the horse has fused and thickened its lower bones to withstand the impact of running. This diagram beautifully captures how a single structural blueprint was modified to conquer every corner of the earth. Looking at that diagram reinforces the mathematical principles we just calculated. Adaptive radiation is nature's way of taking a single successful blueprint and modifying it to conquer new environments. By simply tweaking the lengths and thicknesses of the pentadactyl limb bones, mammals have evolved to run, fly, swim, and dig with incredible efficiency. The mathematical principles of levers show us exactly how these physical changes optimize a limb for either speed or power. You cannot have both. There is always an evolutionary trade-off. Ultimately, this concept beautifully illustrates that the vast diversity of life we see today is deeply connected by shared ancestry and clever mechanical adaptations. We have covered a lot of ground today, so let us summarize the key takeaways. First, we learned that adaptive radiation is the rapid diversification of a single ancestral line into many specialized forms to fill new environmental niches. Second, we saw that all mammals share the same foundational pentadactyl limb structure, proving descent with modification. Third, we discovered that these limbs act as biological levers, and by calculating the mechanical advantage, we can mathematically prove whether a limb is adapted for the extreme speed of a cheetah or the raw power of a badger. You now have a solid understanding of how physics and biology combine to shape the diversity of mammals.